This is Cameron Chai from Azonano, and I'm bringing you another episode of azonano.com TV, and today I'm speaking to Roger Proksch from Asylum Research, and he's going to tell us about their Cypher AFM with electrochemical strain microscopy technology.
Thanks a lot, Cameron. I'm standing here at the MRS show at our booth in front of the Cypher AFM, which we introduced 2 years ago at this very same show. We've recently added new capabilities to this microscope, a technique called electrochemical strain microscopy, which leverages a lot of our advanced techniques on piezo force microscopy to measure lithium ion transport in battery materials. I'm going to let Sergey Kalinin from Oak Ridge National Lab, the laboratory that developed this technique, tell you a little bit more.
Thank you very much, Roger. So basically what we tried to do was to develop a method that allows us to study the electrochemical phenomena in solids on the nanometer scale. So it is very well known that lithium-ion batteries or fuel cells are tremendous markets and tremendous opportunity for both applied and fundamental research. The problem is that if we want to understand those materials and make them tick, we really need to study them not on the level of the device when we have a battery, but on the level of the sort of several grains, or one grain, maybe one plane of the grain, or even a single defect. The problem is that the classical electrochemical techniques that measure electronic Faraday currents, they do not allow to work on the small volumes of the material. So what we tried to do was to come up with the idea of sort of STM, but STM which measures not electron currents, but the currents of ions. And what we use is the fact that ionic currents strongly coupled to the lattice volume. If we apply bias and make ions move inside the material, the surface will expand and contract. And we can measure this expansion and contraction down to a few nanometers, down to a few picometers, sorry. And a simple example is that if we have a conventional material such as lithium cobaltate, if we extract just 10% of lithium atoms from just one unit cell, it generates the strain that can already be measured by an AFM. So this is the gist of it. So by measuring electrochemical strains, we can detect electrochemical reactions at volumes which are a billion times smaller than conventional methods. Everything else is engineering. Engineering took us 5 years, and it's sort of heavily involves a lot of collaboration with folks at Asylum, for whom it sort of took much more. But this is sort of the crux of this development. So we have an example of the image when we have very strong electromechanical response in one grain, and we have no electromechanical response in the other grain. And this electrochemical response comes from lithium ions moving within this grain and not moving in this grain. And what was even more wonderful for us is that we come to this meeting, and all of a sudden Roger and his merry men can make this technique work on the microscope right here. And I think Roger can talk about it more.
Thanks a lot, Sergey. What we have here is a lithium cobaltate sample, much like the one that's in the microscope right now. This is a standard battery material. We've put that material in the microscope. You can see it here, and there's a small cantilever positioned above it. Now this image over here shows the topography of that sample, and the color here corresponds to the high frequency lithium dynamics, charging and uncharging as the lithium ions go in and out of that lattice. That's a high frequency measurement, probably made at about a megahertz or something like that. We can alternatively go to a single point on the material, park the probe at that location, sweep the voltage back, and study the slow dynamics here. And so this is the phase, and you can very clearly see the hysteretic behavior of this material. That hysteresis is related directly to the time constant of the ions moving inside and outside of that material.
And what applications do you see for this technology?
We see the obvious ones of battery storage devices. Of course, that's an area that is an incredibly large market, and we think this is maybe the only technique that will be able to give people information on a nanoscale, on the nanoscale for these materials.
So you think for things like developing batteries for cars?
Definitely for
like
developing batteries for things like fuel cells, it's also applicable. So a lot of materials that are very important in energy storage.
So you think there's got a massive potential for this particular technology then?
We sure hope so.
All right then, Roger, if anybody wants any more information about this technology, they can find that on your website, can they?
Please do.
And your web address is?
www.asylumresearch.com.
All right, Roger, thanks very much to you and Sergey for telling us about your new technology.
All right, thanks a lot, Cameron.